giant tentacles, tens of meters long, capable of snapping ships in half. A powerful maw, able to bite through wood like a hot knife through butter. A monstrous titan, strong enough to drag even the largest of ships down into the watery depths. The Kraken is a legend that's been passed on for hundreds of years by sailors. But today, we know that these legends are actually based on sightings of the colossal squid. Have you ever wondered how a colossal squid could even grow that long? Or maybe if it's possible for other giant monsters to be lurking in the depths? Well, the simple answer to that is yes. The vast majority of the oceans are unexplored, and there exists a phenomenon known as deep sea gigantism. Deep sea gigantism is the tendency for deep sea species to grow far larger than their shallower water counterparts. So, I've always been fascinated by the deep sea and different types of creatures down there. And so I've done extensive research on deep sea gigantism and the different concepts and principles behind it. So the deep sea is a harsh environment that deep sea creatures have grown larger to adapt to. So I'll first begin with an overview of the deep sea. What exactly is the deep sea? Introduction to the environment and the conditions down there. And then I'll follow up with Kleiber's law and Bergman's rule. And I will end on why being larger is beneficial. So let's start with a brief introduction to the deep sea. The term deep sea is used past the depth of anything past the depth of 200 meters or 660 feet. At 200 meters, the sunlight begins to dramatically drop. And at 1,000 meters, there's actually no sunlight at all. This means that plants that depend on photosynthesis to create their own food and get energy disappear completely. And this causes the amount of food there is at that depth to plummet completely. That lack of light also means that the temperatures will also drop dramatically. At 200 meters, the temperature drops below 41 degrees Fahrenheit, and at 1,000 meters, it drops as low as 32 degrees Fahrenheit. At great depths, there will also be a lot of water pressure, but fish are actually completely unaffected by this water pressure. Water pressure only affects substances that can be compressed, like gases like oxygen, but fishes are mostly composed of water, which can be crushed or compressed. They also contain an organic compound known as trimethylamine and oxide, which helps protect them against the cold and the water pressure. Now that I've talked a bit about the deep sea, I will next be talking about Kleiber's law and Bergman's rule. So the two main rules behind deep sea gigantism are Kleiber's law and Bergman's rule. As said in the second edition of the Encyclopedia of Popular Science, published in 2013, Bergman's rule states that larger species are found in colder climates, while smaller ones are generally found in warmer climates. An example of this is marine cephalopods, copepods. Marine copepods are tiny crustaceans. They're usually 1/32 of an inch to 3/32 of an inch. But in polar regions, they have been found to be as large as half an inch, which is 5 to 6 times larger. Now, this is primarily because larger body masses mean a greater ratio of volume to surface area. This means that they have better heat retention, they lose heat less slowly, which helps them regulate their bodies easier and conserves a lot of energy in cold environments. Kleiber's law is named after Max Kleiber, a biologist who's known for his work. And in a 2015 article titled Kleiber's Law, How the Fire of Life Ignited Debate, Field Theory, and Neglected Plants as Model Organisms by Carl J. Nicholas, professor at Cornell University, and German evolutionary biologist Ulrich Fitzgerald, it's explained that for the majority of animals, the metabolic rate is actually equal to their mass to the power of 3/4. this graph, the line is the formula up there, and you can see how various types of animals line up with the formula. Now this means that an animal with a mass of 10 grams compared to an animal with 100 grams, that animal with the mass of 100 grams will only have a metabolic rate that is 5.6 times greater, even though it has 10 times more mass. This means that even though the metabolic rate, total metabolic rate may be higher, the rate per unit is actually lower. Larger animals are more efficient. Next, I'll be talking about other reasons why being larger is beneficial in the deep sea. Larger bodies benefit animals in the deep sea environment. As stated in Deep, Diverse, and Definitely Different, Unique Attributes of the World's Largest Ecosystem by a marine ecologist from Minnesota and others in 2010, deep sea food resources are extremely limited. Creatures must adapt to conserve as much energy as possible. Their larger animals' higher metabolism rates help them more efficiently process food and utilize the energy they get. But the lower rate per unit of volume means that they're more efficient in actually using their energy. And this is critical for sustaining their basic life functions. Larger animals will also have greater reserves of energy on their bodies, which is extremely helpful during times of scarcity for food. Now in conclusion, today I've covered deep sea environments and conditions, described Clybur's law and Bergman's rule, and ended on benefits of actually being larger. The deep sea is a harsh environment that animals have grown larger to adapt to. Now that we know that deep sea creatures can grow so large and why, I can't help but wonder what other titans like the colossal squid exist in the depths. What other giant monsters worthy of becoming the next myths for the hundreds of years to come exist in the abyss.